So I'm just opening the chat window so that, yeah.
Colombia is playing today against Argentina for the American Cup, so it's very exciting.
Pretty cool, yeah. Pretty cool. Yeah, 2 tournaments are going on, you know. There's a lot of excitement in the Euro Cup as well.
Yes, exactly. No, what I'm talking about is both the Euro Cup and the Copa America. They're both
Copa America, yeah.
Yes. Italy versus Spain. Spain today. Okay, great. Yes.
Yeah, we've got Spanish and Italians in our group, so wait until tomorrow. So
yeah, so yeah, Italy's playing Spain today, and a few years back, Emily and I were in Spain, and we got to see live Italy-Spain. It was fantastic. Yeah, there's a chatter about, of course, Stanley Cup final is going on. You guys are hockey fans, but last night was a spectacular game. So one team, the Montreal Canadiens, was supposed to be eliminated. They were being almost swept, but then they pulled out an overtime, a spectacular win. So it's kind of fantastic. And my son tells me tickets are going for like $11,000 or something. Okay, so we're almost at 50, so I think maybe we should start. So today we have a pleasure of Antoine Browaeys continuing on telling us about Rydberg atoms in optical tweezers as his second lecture. So take it away, Antoine.
Thank you. So hello, everyone. So yes, indeed, the second lecture on Rydberg atoms in optical tweezers. So yesterday, what we've done was to, try to recap what we've learned yesterday. So yesterday, what we've learned is some kind of toy model that introduced the idea that if you get an atom or 2 atoms, each you can consider as ground and excited state, no matter what the state are, it's very important, they may be the actual ground state of an atom, or they can be an excited state that you do consider as your ground state or the ground state of the 2-level system. And so once again, bear in mind, it's not necessarily only for a ground state atom and an excited atom. It's just in all the manifold or in the states that you have, you may pick up 2 of them, call it G and E. Okay, and so what we've learned is that, of course, they interact through a dipole-dipole interaction, which we wrote D1, D2 over R cube. Those are operators. And we have derived the kind of interactions that they can have, essentially saying that they could have either a van der Waals interaction, so C6 over R6, that would be for EEGG, or you could have 2 degenerate states that led to longer range interactions. So my drawing is a bit horrible from this point of view, but essentially a different power law, C3 over R3. So that's what we learned yesterday. And so essentially, yesterday I just pronounced the word Rydberg at the end, but we haven't said too much about that. And today we're going to dive a bit more into the topic and try to merge two concepts that are the one of trapping atoms in what is called an optical tweezer in order to create arrays of atoms. And in these arrays of atoms that you can see here on this slide, so each of the bright dot corresponds to one and only one atom. Of course, we will give you more details about that. The typical distance between the atoms is on the order of several micrometers. So it means that if I have one atom in one trap and another atom in another trap, separated by a few micrometers, essentially they do not interact. In the ground state, the interaction is totally negligible at such a large distance. So the idea is to merge this concept of arrays of tweezers with a second important concept, which is Rydberg interaction. So you would promote the atoms to Rydberg state, and there the dipoles that you induce will be gigantic in a sense. And the consequence is the fact that you can have a significant interaction at a micrometer distance. And the interactions we will encounter between two Rydberg atoms are exactly the one that we discussed yesterday, either the van der Waals interactions or the resonant interactions. Okay, and so I will try to describe that today. So this is the outline of the talk. I'm not entirely sure I'll be able to cover the fourth part, but essentially I will give you some experimental considerations around how you can trap atoms, and in particular individual atoms, in what is called a tweezer, which is a laser beam tightly focused, and how you can arrange them in arrays. So I will, so it will be pretty descriptive. I'll do a bit of theory, but reasonably simple one. And then we'll dive into a Rydbergology, which is to say we'll try to discuss the properties of Rydberg atoms, the scaling, their interactions, and we'll introduce an important concept which is called the Rydberg blockade that is very useful for many body physics. And then I will show you essentially kind of textbook experiment where you can measure the interactions between exactly two atoms. And the reason why I want to do that with just two atoms today is because it will already give you all the ingredients to go to the many body physics that we will do tomorrow with this platform. Okay, so yesterday the lecture was fairly general. Any atoms, as long as you consider two same atoms, rubidium, sodium, or whatever. Today we're going to dive more into the specificity of Rydberg atoms.
Antoine,
Okay.
Can I just interrupt for a second and ask a question?
Of course. Yep.
Yeah. So I just want to make sure I understand. For the 1 over to the 6. You don't need a permanent electric dipole moment. That just comes from fluctuation. So, yes. But for the 1 over r cubed, do you need
for the 1 over r cube, you need to have two states with opposite parity that are coupled. So PS, SP, and essentially you have a coupling. So it's just because there is a matrix element, SP d1, d2 over r cube, PS. Okay, this is the degeneracy, and those two states are coupled by this, and essentially just d square, because the two matrix element SP, S d1 P is equal to P d1 S.
There's no permanent dipole moment without that.
There is never a permanent dipole moment if you place the atom. So P d1.
Yeah, it's just because it's fixed parity. Yeah, it's 0. Yeah.
Yes. And the same.
This is only in the absence of an electric field. Yes, in principle, you add an electric field.
This is in the absence of an electric field. If now you add an electric field, the kind of thing that you would have is an electric field would couple a bit of S and P. So let's assume you put an E, let's call it E naught, it's a DC field. What this Hamiltonian will do, it will create a superposition S, which in perturbation theory is essentially your S plus an admixture of D E naught over the energy difference, H bar omega naught, times P. And this new state now, S till whatever it is, ds is non-zero,
right?
Because I have admixed two states of different varieties. And this is a permanent permanent electric dipole. And
so my
really
question was, if you don't have Rydberg atoms, the statement is just you have this C3 over R cubed. It's just the C3 coefficient is tiny. Is that how I should think of it?
Yeah, that's correct. Yes, but I mean, that's correct. Yes.
That when you showed your array, and if I just populate it with regular non-Rydberg atoms in non-Rydberg states, they're still in principle this 1 over R cubed interaction. And even though it's kind of long range, it's power law, the coefficient is very tiny. So is that a correct statement?
That's
Okay.
a correct statement. So just to give you an order of magnitude, if I just take 2 rubidium atoms and I place them at, let's say, 5 micrometer, and this is just a very rough order of magnitude because I don't remember the exact digit, but essentially the C6 over R6 that you would have at such a distance is on the order of 0.1 hertz if you convert that into energy. The C3 over R3, which you would have if one atom would be in S, the ground state, and P on the first optical transition, would be a bit larger, but not by much.
Okay.
So the thing which is,
Okay,
you
makes
have
sense.
a little bit of magnetic dipole too, but of the order of 1 magneton. Yes, depends also on the distance.
The thing which is, so you're asking an interesting question. Let me just, so something maybe I haven't said yesterday, but so you remember the C6 over R6 that I have derived for this 2-level model, this toy model of 2 atoms with h bar omega naught. Oops. Sorry. Is d over r cubed square 2 times h bar omega naught. The C3 over R3 is d square over r cubed directly. So in a sense, this C6 over R6 can always be seen as a C3 over R3 times the ratio of the C3 over R3 divided by h bar omega naught. And this is usually extremely small on an optical transition. It's much smaller than 1 because, I mean, typically assume you got 1 EV of optical transition, which corresponds to 400 terahertz or something like that. The dipole-dipole interaction, the C3 over R3, even if it is on the order of, let's say, I mean, I don't know, a few hertz, you see that this ratio here is going to be tiny. This would be the energy shift of 2 atoms placed in the ground state GG. So let's say 5s, 5s. This will be shifted by this C3 over R3. While if I have an S and a P, that would give rise to the energy spacing in C3 over R3. So you never have C3 over R3 if the 2 atoms are placed in the same state. You do need to have 2 states with opposite parity. 1 atom is in a given state, the other one is in another state.
Sorry, you wrote GG, that's downward shifted by C6 over R6, no?
I'm sorry. Yeah. This is use. Sorry, exactly what the mistake I shouldn't have done.
Yeah. I don't want to interrupt too much. I mean, but in principle, there is the magnetic dipoles that can be.
Yeah. There is. You're completely right. On top of this, you also have a mu b square over r cube, and that's true for alkalis, for example, because the alkalis have permanent magnetic moment in their ground state. But this is even smaller, or on the order of the C6 over R6, actually, for the typical distance that we care about.
But on the previous slide where you showed the estimate for the, right here, you said it's a 1/10 of a hertz, but you said it's for Rydberg in these arrays.
No, this is for ground state atom.
Oh, rubidium. It's not Rydberg, it's rubidium. Okay, thank you.
Yes, rubidium.
As opposed to the Rydberg that you're going to be discussing.
Yeah. The Rydberg, we're going to see that later today. But if I just take n equal like 50, the interaction can be tens of megahertz. It's greatly enhanced, actually.
Beautiful, beautiful. Thank you.
Okay. So, yeah, so let me start with a bit of plumbing and how we can create those arrays of traps. So the first thing we need to remember is how we trap atoms with light. Okay, so essentially the classical vision of this is the usual one. You send a laser beam. A laser beam is an oscillating field, and this oscillating field is going to induce a dipole. Okay, so now you also probably remember from your ENM class this model of an atom, which is essentially an electron, which is elastically bound to a nucleus. Okay, and it means that actually you can write some kind of equations like Newton's law, x being this axis, where mx dot dot is minus the spring constant. You may or not, and for what we're going to discuss, I don't need to write it, add an x dot, which is kind of a friction force. And you've got, of course, the electric field of the laser that drives all this, and that varies as a function of time. So based on that, you can derive the expression of the polarizability of an atom. And the polarizability, you find that this is something that varies like q square over m divided by omega 0 square minus omega square minus an I omega gamma, which is the friction force, which usually we put in there. Oops. Is that clear, this?
Mm-hmm.
Okay. So now if I want to plot if I am working very far from resonance, so omega minus omega naught is much larger than gamma, so much larger than the resonance, essentially the polarizability is 1 omega 0 square minus omega square. Okay, so it means it's almost a real number, so there is almost no friction if you are somewhere in the wing. So this is this function that I have represented here, right? So now, of course, if you have the dipole, which is induced, it's going to interact with the field in such a way that it's a polarizable dipole. So you will have an interaction energy, which is 1 minus 1/2 of d times E. Okay. And as d is proportional to E, essentially you have something which is minus alpha E squared. So now, depending on the sign, okay, the feeling that this thing is, oops, no. Depending on the sign of alpha, you may be trapped, or you may have the lowest energy either where the intensity is the largest or where the intensity is the highest. So essentially, if alpha is positive, you will be trapped, or U is minimal, when E square is maximal. And to have alpha positive, you need to be on what is called the red side of the resonance. So the frequency of the laser has to be below resonance. On the contrary, if alpha is negative, then you will find that U is minimum, where E square is minimum. So there is the high field seeker and the low field seeker, if you wish. Of course, all this is only true if you work away from the atomic resonance, because if you are too close to the atomic resonance, there is another thing that occurs, which is the fact that this friction force will act and therefore will create, in a sense, spontaneous emission. Okay, and you want to avoid that. You want to have a conservative potential. The conservative potential is obtained when you work away from the resonance. And the reason why it can work is this friction force, which is the imaginary part, if you wish, of the polarizability, varies like in the wing, omega minus omega naught square in the wings. And therefore, you can kill the imaginary part without killing too much the real part. And therefore, you can trap. I mean, of course, you decrease the amplitude of the trapping, but still you can decrease without almost any friction. So that's the first important thing that's called optical trapping. Okay? Right, so this is the purely classical vision. I've never said anything quantum. Of course, you can view it also from a quantum point of view. And the quantum point of view is the following one. Once again, take a two-level system. This two-level system, you apply an electric field as it is represented here. So essentially a laser that couples the ground to the excited state. And what the light is going to do, it's going to shift the ground state. So this is what is called an AC star shift. Why do you have that? Well, assume that you write the Hamiltonian of the field and together with this two-level system, you would have something in what is called the rotative wave basis, so delta being the detuning, which you will write like this, omega over 2 minus delta. So maybe it reminds you of something, but essentially, this is a matrix that we encountered yesterday. And we know that the ground state, delta E of the ground state, is shifted by omega over 2 square divided by delta, which is again exactly the same kind of expression as this, because omega, the Rabi frequency, is directly proportional to E. So this is nothing but dE square divided by omega minus omega naught. And you recover the expression, the classical expression. So you see two visions of what is a dipole trap, either a classical or a quantum vision. Of course, they give the same result. Okay. Right, so now, let me just emphasize one thing is that unfortunately, the thing which is hard to do is to create optical traps that are deep. Okay, so essentially, if you just use a regular laser, it is able to create a depth of the trap. I'm going to discuss that in a minute, but only on the order of a few millikelvin if you use like a watt of laser power focused over 1 micrometer. Okay, and so typically a power of about, let's say, 1 watt focused over 100 micrometer will give you a trap depth, which is around here. So you need to start from laser-cooled atoms. Okay, otherwise you cannot trap them in an optical field. And so I'm not going to discuss laser cooling per se, because of course, this is what Eric explained to you yesterday. So this is the initial step that you need to go through if you want to create, to be able to trap atoms in these conservative traps. Okay, so the thing that I want to discuss now is how we can trap in 3 dimensions just using one laser beam. And this is the concept of optical tweezers. So now if you take a real laser as the one that we use in presentations, the profile, the spatial profile is what is called a Gaussian beam. So a Gaussian beam means that around a point where you focus the light, the typical size of the beam waist, of the intensity maximum, if you wish, so that's the beam that you focus, is focused on a size which is called the waist, W, and there is a typical range of variation of the intensity along this direction, which is given by what is called the Rayleigh distance, which essentially is the ratio of the waist square by the wavelength. Okay, so this is generic of any Gaussian beam. But so now, if you manage to focus your light on a spot size here, W, which is on the order of lambda, you see that now the intensity varies, the typical range of variation of the intensity. So you've got this along this axis and something like this along this axis. The intensity is now the largest and kind of concentrated over a size which is typically lambda here and pi times lambda here. So the meaning of that is that now if I take an atom and I shine a laser, which is readily tuned with respect to the transition, the atom is going to look for the place where the intensity is the largest, and it's going to get confined in a typical potential, which has a size of lambda cubed. Okay, so that's the first important concept. A single beam, because it's so tightly focused in one direction, it's also focused in the third direction, and that ensures a variation of the intensity of a volume, which is lambda cubed. Okay. All right. So this
Antoine,
is how we do it. Sure.
Antoine, there's a question in the chat
sorry.
by Francisco. Maybe you want to address it. It's in the previous slide.
Yeah. Sorry, I should have looked at the chat at the same time.
No, it's okay.
So the question is, can you explain a bit more why the dissipative force is bad for us? It is bad for us because it leads to heating. Okay, so essentially, if you place an atom in your dipole trap, okay, so now I'm going to plot essentially along one direction. So for example, this one, it's a 1D representation. It's a function of X. And I have an atom here, okay? So now if this laser, which creates the trapping, at the same time makes the atom emit light. Oops. Okay, so essentially the atoms emit photons induced by the fact that induced by the laser beam itself. Then it's going to hit the atoms away from the trap, because each time it spits a photon, it has a recoil. So essentially the energy E dot as a function of time going to be something on the order of the recoil energy that Eric introduced to you yesterday times the scattering rate.
Mm-hmm.
So it means that you can no longer keep for a long time the atoms in the tweezer because it's going to be heated out of the trap. Does it answer your question, Francisco?
Yes. Yes. Thank you.
Okay. All right. So let's look at it in practice. So the first time this kind of technique of optical tweezer has been used for neutral atoms, and this is something which is very popular in biophysics, but for neutral atoms, it was done the first time by Philippe Drangier, actually at the Institut Optical, and then I joined the group and we improved this platform. But essentially, the way it works is summarized here. So you have somewhere in vacuum or not in vacuum, it's totally irrelevant here, but you've got a lens, which is a pretty good lens. Here we use a single lens, which has special design so that you minimize the aberration of the lens, and you can focus the light down to a size which is on the order of lambda, the wavelength. So typically, the waste is given by the wavelength of the light you use times 2 times the numerical aperture of the lens. So you need to have a lens which is as open and as with a higher numerical aperture as possible. Okay, and so here in the focal plane, you will have the intensity maximum, okay, and that's where you're going to load the atoms. So in order to load the atoms, as I was saying, you need to start from laser-cooled atoms. So the kind of thing we start from in this experiment is that we create a cloud of cold atoms that have been laser cooled. In our case, I will illustrate on rubidium. Typical temperature you start with is 100 microK, which is 1/10 of the trap depth. And essentially, what we have is that we've got 2 kinds of laser beam. We've got the laser beam that are very far from the resonance. So I use rubidium. Rubidium has a transition at 780 nanometer and 795. But the light I use for the trapping now is well detuned, it's 850. So essentially this light doesn't induce any fluorescence. On the other hand, the cooling light, this one, is at 780 nanometer. It has to be near resonance so that you induce the cooling on this transition. So you've got 2 kinds of laser, the one that makes the atom fluoresce and that ensures the cooling, and the one that do not make the atom fluoresce and that ensures the trapping. Okay, and so at the same time as the atom fluoresce in this tweezer, but they are fluoresced by counter-propagating lasers, so they do not hit, just to answer Francisco, who was just wondering why dissipation is bad. Dissipation is bad unless you use it in a cooling configuration. And so if you have 2 counter-propagating lasers, you can prevent the laser from hitting, the atoms from hitting. So you can collect on a CCD camera, essentially, the fluorescence light emitted by the atoms. And so you will, if you zoom in on a given pixel, as a function of time, this is the kind of signal that you observe. So this is what you observe on the CCD camera. So you've got some baseline, so background, essentially, very few photons emitted or collected per second. And then suddenly there is a jump in the signal. And then after some time, you go back down. So what happens here, really? So what happens here is that at some point, you've got the dipole trap. An atom enters in the dipole trap. And because you've got the cooling light, it enters, but it is going to be slowed down gently and stays at the bottom. Okay, that's what happens here. So suddenly the atoms arrive, it stays in the same place, and you can accumulate the fluorescence and measure it on the CCD camera. So now what happens when we arrive here? What happens when we arrive here is that you already have your first atom, which is trapped. And then there is a second atom which tries to enter. Okay, it is slowed down as well in the presence of the light. So suddenly it arrives here, and you've got 2 atoms that are nearby. And those 2 atoms are going to undergo a very exoenergetic collisions induced by lasers. And essentially, this pair of atoms will pick up a lot of kinetic energy and be expelled from the trap. And this is a nice illustration of the 2 kinds of potential that we discussed yesterday. So let me try just to show you a bit more in details, if I manage. What is the mechanism? The mechanism for this
Anton,
is,
there is another question in the chat that is about the fluorescence. Does fluorescence induce that heating you were just referring to?
yeah, so that's a very good question again. So remember, we've got the first configuration. I just take a laser beam and I focus, okay? So essentially, I create a trap. If I only have one laser beam, okay, this single laser beam is going to push always in the same direction the atom. So h bar k is the direction of this. So essentially, what the atom says is that it always receives kicks in the same direction, and at the same time, it will randomly expel or eject spontaneously emitted photons. So the atoms is going to hit out of the trap because there is one beam. If now I just take two beams counterpropagating, those two beams, as Eric explained to you yesterday, if you work below the resonance, they will induce a friction force minus alpha times V. So you will at the same time hit the atoms due to spontaneous emission, but what this force configuration does, oops, sorry, just trying to get the pen, it's going to cool down by this friction force. So you've got two competing things, the heating due to spontaneous emission and the cooling due to the configuration of two counterpropagating beams. Okay? So the 780 nanometer laser make the atom fluoresce. They are close to the atomic resonance, slightly below. The 850 is very far from the resonance, but can still induce a little bit in order not to induce fluorescence. Is that clear or not? So who has the question? It's Alex, right? Alex, is it clear?
Garrett. It's Garrett, I think.
Oh, it's Garrett, sorry.
Yeah,
Garrett,
Alex has another question after, yeah.
Makes sense.
Yeah, it makes sense. I mean, in fact, isn't that what Eric used to derive the limit on cooling using
That's exactly that. If you do that, the balance cooling versus heating give you what is called the Doppler temperature, which is on the order of h bar gamma, where gamma is the line width of this transition.
Yeah.
Okay. What is that second peak on the fluorescence plot? This one?
Yeah.
Is it the one you're talking about, or Alex? Yes, but it's another atom which has entered. So essentially, here you have an atom enters in the trap, it slows down. That's what happens here. Here you've got the second atom that enters, and suddenly you lose the two of them at the same time. And here you've got another atom which enters in the trap and kicks out, which enters in the trap. And again, here, the second atom enters and the two gets kicked out. Okay? So the thing I wanted to explain you is why do you have these atoms kicked out when they are in the dipole trap? And so maybe it's becoming a bit too complicated, but okay. I remind you, we've got two atoms. Each of the two atoms can be in the ground state, which I will call S, and there will be a first optical transition, which I will reaching a state which I will call P. So this is the 780 nanometer transition for rubidium. So now, what did we learn yesterday? We learned that the interaction energy between this pair of atoms is first in the ground state C6 over R6 with a minus sign. But now that corresponds to the case where the two atoms, each of them are in their ground state S. And then we've got this huge potential, 7 at a transition which corresponds to a wavelength of 780 nanometer. Okay, so now this corresponds to one atom being in S, the other one in P asymptotically. So those two atoms arrive in the dipole trap, and in the presence of the cooling light, they're going to get excited. But they are not excited on the potential, which is a long-range potential. So they're going to get accelerated towards each other. So they will gain kinetic energy in their center of mass. But at some point, this molecule is to decay back to the ground state. It decays back to the ground state in a typical time, which is typically the inverse of the lifetime of this guy, which is typically 20 nanoseconds. But in 20 nanoseconds, it has gained a lot of kinetic energy along the potential curve, and essentially, this kinetic energy is much, much higher. So it's typically a Kelvin of kinetic energy that you pick up. And therefore, it's much larger than the typical millikelvin of the trap depth. Therefore, you lose the atoms. They cannot stay trapped any longer. So you see, this is already an illustration of the interaction we discussed yesterday. As soon as one of the two atoms is excited, they do no longer interact via van der Waals interaction, but through resonant dipole-dipole interactions. Okay? Good. So what are the atoms that people have trapped so far? This is the periodic table, and essentially the atoms in green and red are the ones that have been laser cooled, and the ones in red are the ones that have been trapped in individual trap, the way I described that. Okay? So you can see there are like sodium, rubidium, cesium, strontium, chromium, and also erbium and ytterbium quite recent. Okay, but so now the kind of thing we want to do many body physics is to have many of these traps. So the way we can have many of these traps is by doing diffraction. So the idea is extremely simple. The idea is that in front of the lens that generates the dipole trap, I will place a diffraction grating. So what is going to be the influence of the diffraction grating? I mean, in the focal plane of the lens, instead of having just one single trap, now I will have many diffraction orders. I will have the +1 diffraction order, the -1 diffraction order, the zeros, and so on. And so now if you use a proper diffraction tool, then you will be able to create arrays with any geometry, so spots arranged in any geometries. So essentially, what Fourier optics tells you is that in the focal plane, before the trapping laser arrives in the chamber, arrives on the lens, you place a device that writes a phase. So essentially, this device writes a phase IFX that can vary from place to place. Diffraction optics tells us that what you have here in the focal planes is nothing but the Fourier transform of the phase factor, modulus square. So you see that if you want to have a given geometry of the arrangement of the orders, of the diffraction order, you just need to calculate the proper phase so that you can create the geometry you want. So this is an example that you have here of the phase in 2D that is generated by a liquid crystal device. And so this liquid crystal device imprints a phase that varies from place to place. And if you look in the focal plane, in this plane, we just place a camera here to look. This is the array of spots that is just the Fourier transform of this phase factor. So this is the way it works. So to generate arrays, the best way is to use diffraction. Does it make sense? Okay. There are a few subtleties, but I'm not going to that too much in detail. But so now,
this is sorry, Antoine. So this is diffraction as opposed to, I mean, kind of another way to maybe a simpler realization of this. And I mean, ultimately, still diffraction is, you interfere counter-propagating laser beams and create an optical trap. So can you contrast that technique with this technique, with the electro-optical light modulator?
So indeed. So let me just check something.
If it takes you too far afield, then feel free to punt on this question. But it'd be nice to, because a lot of times we hear about this.
Well, so what is an optical lattice? Essentially, the optical lattice is what you're describing. So the optical lattice is another way to do optical trapping, but now you rely on interferences of counter-propagating laser.
Right, I see.
So it's a very fruitful method, obviously. I mean, optical lattice is used in many, many groups. There is just one drawback, is that necessarily the distance between the atoms is on the order of the wavelength of the light, which can be great, actually, because it allows the atoms to be close to each other. But the geometry is set by the arrangement of the laser beam. So for example, if you want to create the Kagome lattice I was actually showing to you a minute ago, it's extremely challenging to do that by interfering laser beams. So this technique with the SLMs allows you any arbitrary geometry.
I see.
which is much harder with an optical lattice because it's necessarily, you have some constraint due to the optical axis you have on the experiment.
So has this technique in practice now surpassed and just
yeah. So I will show you. Yes. So optical lattice, you will hear a lot about that during all those set of lectures, but from Emmanuel Bloch, for example. But so the tweezer is a bit newer technique to do.
But I guess what I'm asking is a terminology. When people say optical, I'm a theorist, so when I hear optical lattice, I don't care
optical
how you made
it. Optical lattice means really interfering laser beams.
Okay, it does not mean. Okay, it does not mean doing this electro-optic light.
No, this is really arrays of tweezer, and it's a holographic technique.
Oh, I see. So why would anybody now do optical lattice if you have this?
Because you've got many cases where you want the atoms to be at lambda distance. I mean, with this technique, the typical separation that you have is rather in the range 2 to whatever, 20 micrometer.
I see. Thank you very much. Okay.
Yeah.
Antoine, sorry, you do have another question in the chat.
Yeah. So should we turn off the cooling light after an atoms are trapped? Yes. As soon as an atom is trapped, what we do in practice, we switch off the cooling light, and then the atom stays in the trap for about 20 seconds until it's kicked out, usually by a background collision from the residual gas in the chamber.
Okay.
Can I ask you a quick question about tweezers?
Sure.
So when you were just talking about like lattices versus tweezer arrays, I was thinking about how you would make like a quasi-crystal lattice, like what Uli Schneider does with tweezer arrays. Just because since like along like an axis in a quasi-crystal, the gaps between the diffraction peaks that you would see can be sort of any value. It seems like sometimes you would get peaks that should be separated like much less than the wavelength. I didn't know if like using an SLM to make.
No, people have done quasi-crystals. Huh? There's no problem.
With tweezers arrays.
Yeah, you can do that.
With tweezer arrays?
With tweezer arrays, yes. You had a group did that early this year, yeah. A group in Strasbourg in France, yeah.
Okay, so it's not a problem. Okay.
Yeah.
But Charles probably has a good point. It means you would have a cutoff on the shorter scale. Like you wouldn't. It wouldn't truly be a quasi-periodic in the sense of shorter.
No, but I mean, it will always be finite size anyway, but you would be, I mean, let me move on and show you that we can generate almost any arbitrary pattern. So the quasi-crystal is actually certainly one of them. So we haven't done it in our group, but that's something we could do, yeah. Of course, I mean, if you want to decide that it's a quasi-crystal, you need to have enough elementary cell to decide that it's not periodic.
Exactly.
Why with tweezer arrays of tweezer, probably you can also easily create finite system with sharp edges without using box potential. Yes, I guess so. Yeah, sure. Yeah. So what limits the distance between lattice point in this case to about 20 microns? Nothing. When I say 20, it's in our setup. You could go to 50 or 100 if you wish.
No, but what they mean is why can you not get to the optical, to the wavelength scale?
The wavelength can is more a problem because the typical size of the tweezer themselves is on the order of lambda. So it's very tricky to separate them by lambda because essentially you cannot resolve them any longer. Plus there are a few technological issues that prevent you from going too close, but people are trying actually. Okay. All right. So now the drawback that we have with this method is that how do you load the array? Because the problem with this system here is that if you just take a picture at a given time, because it's a random loading of each of the tweezer, you do not have all the traps filled at the same time. Okay, you essentially have one half of the trap that are filled at a given time. That is clear for everyone, because you've got the probability. I mean, remember, there is this entrance of the atoms in the tweezer, which is totally random. So at the end of the day, if you have in average, the tweezer is filled half of the time. And therefore, if you just take an array of, let's say, 10 by 10 here, so it means each of the square would correspond to location of a laser beam. You take a picture, and essentially one half of them is trapped. So that was an issue for this platform, because if you want to create arbitrary geometries of the atoms now, not of the tweezers, you need the atoms, the tweezers, to be filled with certainty. And so the solution was given actually by the group of Dieter Meschede more than 10 years ago. The idea is the following. The idea is to take an atom at a given location and carry it to another trap. How do we do that? Well, it's very simple. You just add to these, very simple, so it's reasonably simple, at least in principle. Experimentally, it's a bit more challenging, but on this array here, you will focus on extra laser beam, but this laser beam can move. And therefore, it can pull an atom away from its initial location, bring it to, for example, this location. And so now, if you want to, for example, fill only this part of the array, well, you just need to move the atoms in order to fill completely the array. So you start from a random configuration. You look at where the atoms are to start with. To do that, you take a fluorescence picture of where the atoms are located, and then you move them. So after 14 moves, starting from this initial configuration, you can create these lines of atoms. Or you can create this 1D with periodic condition, this square, this honeycomb lattice, this Kagome type of lattice. Okay? So this is really, so that was what we've done around 2016. But so now the kind of a record of how many atoms we can manipulate. We can manipulate them 200 atoms in 1D, 200 atoms in 2D. You can place them in triangular array. You can place them in any arbitrary pattern that you wish. So this is an example of a completely silly pattern, which actually is a pixelized version of the Mona Lisa. Okay, so it shows you that the control is totally useless for physics, obviously, but it shows you the kind of control we have over the geometry we can create with this thing. Okay, right. So people now are widely using these techniques. And so I'm not going to discuss too many because time is actually running pretty quickly. I don't want to show you too many different techniques. They are all variants of what I have discussed so far. It's all optical tweezers, and then you've got different ways to create the arrays with spatial light modulator, with acousto-optical modulator. Okay. I've given, you will have the notes in any case. You can Google all those groups and you will find the various techniques if you are interested. But they are all exactly based on the principle that I was discussing before. So now the thing which is important to realize that these platforms allow you today to arrange about 200 atoms, and people are working towards a few thousand. Okay. So just as an aside, I'm sorry.
Can I ask a quick question?
Sure.
So when you are seeing these atoms, they're fluorescing, right? But then you also experience loss while fluorescing, right?
Sorry. Can you speak a bit louder because I don't understand the question? Sorry. Yeah.
Oh, sorry. I'm saying when you are seeing these patterns, the atoms are fluorescing, right? And you are shining some resonant fluorescent light on the atoms.
Yes. Yes.
But you also expect loss of the atoms when you are shining fluorescent light, right?
No, because it's the same. It's the cooling configuration. So they are cool at the same time, so they fluoresce.
I see. But when you apply the cooling light, you also see these two-body losses.
Only if you have two atoms, but you only have one.
Okay. I see.
Okay.
Antoine, can you say why are they only fluorescing when they're not in the trap? Are they still fluorescing, or is just they're missing the beam, fluorescent?
The atoms are trapped in their tweezer. In the absence of cooling light, they are in the dark. They do not fluoresce, and they stay at the bottom of the tweezer. So now you shine a laser beam, let's say contrapropagating,
to excite them
at the same time, and then they fluoresce. And then you can collate this fluorescence on the camera.
But what I'm saying is these beams that make them fluoresce, are they focused just on one?
No. They are good. No, they are actually.
They're covering the whole array.
They are covering the whole array. Yeah.
I see. Yeah. But if there's an atom, so suppose there's an atom not in the trap, not in the one of the side of the trap, but in between.
Yeah, but
I don't know.
It's
passing by. It's passing by. Why doesn't it fluoresce?
Because it's passing by very quickly. So it does fluorescence, but it doesn't emit enough photons for you to see. So we have a kind of a background of fluorescence light emitted by all the other atoms. But the ones that are trapped, you know where they are trapped. You can look at this tweezer and the fluorescence get at the pixel, which is imaging.
It's because
But the laser light kick the atoms too. It's half momentum, so it's an optical. So you kick the atoms if you are not trapped too. So
yes, on top of that, you kick them. Yeah, you hit them, but in any case, they pass by and they do not stay always at the same time emitting photons. So essentially, the photons are scattered all over the place.
Yeah. So the ones that are trapped, you're accumulating lots of fluorescent photons from them. That's what it means to see them.
Yeah.
While the ones that are not trapped, you don't accumulate enough photons to see them.
Exactly.
Is that right? Okay.
All right. So these techniques can also work in 3D. This is just an advertisement. I'm not going to spend some time because this would be a full lecture in itself. But okay. So let me move on now because once again, time is flying. So first, do you have any questions so far about what I've said? Before I move to the
there are a couple of questions. Yeah.
Okay.
In the chat, maybe. Okay, or you can go now.
Yeah, I typed my question in the chat, but I can also ask it directly. That's okay.
Yeah, go ahead.
Okay. Is there a lower limit for the size of the tweezer array? So you need 2 micron, but is it just depends on the? Does it just depends on the SLM resolution?
It does depend on. Yes, it depends on the SLM resolution and the resolution of the optics you are using. So typically, in our case, we have found that going well below 2 micrometers is difficult.
Okay, thank you.
Okay.
But it's mainly technology. Yeah.
There are also 2 questions by Daniel and Jackson in the chat.
So you mentioned that the lifetime of a trapped atom is 20 seconds. How long does this kind of loading take? So typically, an atom is loaded. The moving of the atoms from one side to another one takes 1 millisecond. So typically in 20 seconds, you can do 20,000 moves. Okay, so we have a big gap between the time scale associated to the lifetime of an atom in a trap and the time it takes to move them around. Okay.
Yeah.
How about are the trap-induced light shifts? Is it tens of megahertz and you just detune imaging and cooling? I mean, it's yes, about 10 megahertz, and that's enough to actually further detune the laser beam and in this way reach what is called the Sisyphus cooling that actually Eric discussed yesterday. So this is not a problem for the cooling. It actually allows you to get to a lower temperature than if you were in the magneto-optical trap, for example. Does it make sense, Jackson? Or? Okay.
But is the moving of the atoms, to collect them into, to fill up the traps, is that something you do? It's automated, or it's like by hand a student does that?
No. It's fully automated. It's fully automated because you can do that on any arbitrary platform. So the computer looks at where the atoms are, calculate the set of moves that you need to apply,
impressive,
and move the atoms one by one. Yeah.
Wow, impressive. Okay.
Anton, can I ask also, so what about the 3D trapping? It's much more challenging. I mean, the 3D trapping, do you think it's
challenging? It's challenging in the sense that we need to do that plane by plane.
Mm-hmm.
Yes. And therefore, you multiply the duration. So if you want very complicated structure, you will need to sort the first plane, then sort the second plane, and so on. So it's really time consuming.
I see.
So the kind of physics that we could easily access to at the moment, it's bilayer physics. That should be feasible. Going well beyond that, it starts to be challenging. But a lot of groups are working on that. So I'm sure that there will be easier options in the future. But
but in principle, can you combine an optical lattice along the CD direction with tweezers?
Sure. Yeah. No, you could. Okay. You could perfectly. Thanks. And actually, this is a trend that is going on. I mean, Adam Kaufman is trying these kind of things. And yes, and we're trying as well on another setup. Yes. So.
Can I have a question?
Okay. Sure.
Hi, sorry. So I'm sorry if I missed that, but it looks like a pretty universal tool. Are there some limitations to what objects you can trap, or like things you need to worry about, for example, with ultracold molecules? I mean, I know it's possible to trap in tweezers of the ultracold molecules, but are there some special properties we need to worry about when using this tool?
I mean, as far as the moving is concerned, there is nothing special. As long as you can trap them, you can move them around just by adding an extra tweezer, which can move. Okay, so this, in principle, the technique is reasonably universal. I mean, this is a technique that has limitations, and because, of course, you cannot assemble super large arrays because you need to look at where the atoms are and a very complicated pattern of moves that you need to apply. So at some point, you are even limited by the computing capabilities of your driving computer. Right? But I don't see any important limitations. It could be applied to molecules, and ultracold molecules, no problem.
Okay, thanks a lot.
What is the limit of number of atoms in the array? So it's a very good question. So essentially, the problem is the following one. If you have an atom that stays for a time t equal, let's say, 20 seconds in a tweezer, the problem is that now the lifetime of a given number of atoms, n atoms, the configuration with n atom has a lifetime which is t over n. Okay, so now if you have a given number of atoms, then it means that your configuration will last less because, and at the same time, if you want n atoms, you need, roughly speaking, n moves. That takes a times delta t. Okay, so this is this combination of two things that is going to give you the largest number of atoms you want. Because the larger number of atoms you want, the smaller the size, I mean, the lifetime of the configuration, and at the same time, the longer it takes to assemble them. So, and you've got a crossing point which sets the number of atoms, and this typical number of atoms with regular parameter is about 1,000. Okay, so we're not fully there yet, and that's what we're working at the moment in the lab. We're working around the 600. When you assemble them, there are some tricks that you need to play, but yeah. Okay, that answers your question. Okay. So is there an advantage of the phase modulation method instead of imaging an amplitude modulating trapping beam? Yes, the advantage, I would say, is that you do not lose laser power. As soon as you do amplitude modulation, usually you throw away a lot of laser light. And if you want large arrays, you need a lot of laser light. So that's the reason why this holographic technique essentially recycles efficiently all the light you have to send onto it. Does it make sense, Abel? Okay. Good. Let me just move on a bit. So I've done 1/4 of what I had intended to do so far, but that's completely fine, I think. But let's try to arrive at the Rydberg state. So essentially, I will try to tell you a few things about Rydberg that we're going to discuss today. So you will have those slides. So here are a few papers that may be of interest to you if you want to dive more into the details. So what we will consider, just for the sake of simplicity, are atoms from the first column of the periodic table. The reason why I want to do that, although people now start to manipulate strontium and atoms from the second column, is because it's kind of easy to understand by analogy with the hydrogen atom. So essentially, you can see all these atoms as essentially a free electron. So, okay, to a large extent, you can consider your atom as an electronic core and an electron spiraling around. Okay, so if you do that, these are the energy level of rubidium. Okay, just because we use rubidium in the lab, but they will look exactly alike if you are taking sodium, potassium, cesium, or whatever. So this is called the Gautrian diagram. Actually, they are classified as a function of the angular principal, the angular orbit momentum, and the principal quantum number. So Rydberg state, the Rydberg atoms, the first thing to think, to realize that it's not a special atom. There is not in the classification, in the periodic table, something called the Rydberg element. It's just any atoms that you place to a highly excited state is called a Rydberg atoms. So those Rydberg states are usually states with very high principal quantum number. So for the alkali, essentially, you can use your Belov formula that you learned from your undergrad, which is that the energy of the state is, roughly speaking, minus 13.6 eV over n squared. This is a very good approximation. In case of the more complicated alkali, so this is true for hydrogen, of course, but if you have other alkali, it's still reasonably true, at least the functional form, but you have to modify slightly the formula. But what is called a quantum defect. So essentially, you've got the principal quantum number. It looks essentially that this Rydberg constant is the 13.6, but you have to modify that slightly. Why do you need to do that? Because you've got two cases for the for the orbital. Let's assume first L equals 0. And L equals 0, so this is the electronic cloud. You've got the nucleus, the electronic cloud, and now I'm talking about the outer electron. Oops, sorry. The outer electron, if I'm in L equals 0, the outer electron trajectory does that. So it penetrates very violently inside the electronic core. And as a consequence, the fact that it's inside the electronic core is going to see a higher attraction by the nucleus because it's not screened by the outer electronic core, and you've got this correction. On the other hand, if you got L, which is on the order of n-1, you would have a circular trajectory, and therefore the electron never penetrates the electronic core. And to a very good approximation, this is like an hydrogen. So that would correspond to a delta L, the shift, the quantum defect, which is nearly 0, while L, the delta L is on the order of a few, typically it's 3. Okay, so this is a small correction with respect to the hydrogen, but essentially all the properties of the Rydberg, you can think of them as the hydrogen properties, okay, with a small correction. So essentially, the n that you need to use for your Rydberg are the n minus the quantum defect. And there is an n star. And with this, the energy is the same as for the hydrogen, minus 13th over n star squared. Okay, right. So if you want numerical values, saying exactly what I've said, if you are in L equals 0, this is the largest quantum defect, and the higher you get, the less quantum defects you have, because essentially the trajectory avoids the electronic core. And already at 3, you see that the correction is negligible. The thing which is important is that no one knows how to calculate ab initio. People know how to do it, but cannot do it numerically. We cannot calculate those quantities. They are measured. Okay, that's an important thing. This is an experimental quantity, which is known with correct accuracy, but it's not super high either. Okay, so second important property, now that we know that essentially this is the hydrogen atom, is that a Rydberg atom is a huge atom. It's a huge atom in the sense that where does the dependence on G come from? Well, where does the dependence on G come from? It's a good question.
It's not finite structure? I mean, you have to include.
So this is G is the fine structure. This is fine, yes, indeed. And you had mix different L state, for example. So I think this is the reason why it comes, it changes. Does it make sense? Grace? And okay. So once again, the size of a Rydberg atom is huge. It's scaled like the square of the principal quantum number. Okay, so this actually is really huge. So you have on this plot essentially the n squared times n naught. So this is the radius, if you wish, in a classical sense, of the electron, and as a function of the principal quantum number. And I compare on this. So this is something I've taken from a PhD thesis in Germany, and I compare that to various objects. So when you are in the typical Rydberg state that we use in our lab, and in most of the labs are around here. So you see that already the size of a Rydberg atom is the size of a bacteriophage or some kind of virus. So just to give you an example, let's take something which is spoiling our life those days, a COVID thing. It's 125 nanometer. It corresponds to a Rydberg principal quantum number for rubidium, for example, on the order of 60. And so essentially, you would be here. Okay, so the COVID has the same size as a Rydberg atom around n equals 60. Okay, and of course, now if you go around 100, 120, then you become more like a big bacteria. All right, so this is really kind of a macroscopic object, if you wish, almost. It can reach a micrometer size reasonably easy. Okay, so something that I want just to remind you, if I manage, is a very easy way. Yes.
One more
Do we need
question.
to worry about the size? That's an excellent question. In principle, we should, and that is perfectly clear that if the atom starts to be very large with respect to the size of the tweezer, the electron is not going to see the trapping light any longer. Okay. It turns out, and people have done that, looked at that pretty much in detail. Until n equal 100, you do not need to apply any correction to the usual trapping theory that I've given you earlier. It means that essentially the size of the trajectory is still small enough. The Rydberg atoms are larger on a laser wavelength. What is the consequence of this? But this is what I'm saying. And at first, you need to realize that when you look at what is the relevant scale, it's usually, let me get it right. The correction. So essentially, you will need to include on top of the D dot E, you will need to include the quadrupole interactions between the dipole and the electric field. And so Mark Safman at the University of Wisconsin has a paper about that, and he shows that, once again, until n equal 100, the correction is negligible. It's not zero, it does exist. It would start to be non-negligible beyond n equal 100. Okay, so those are all good questions, and people have looked at that in details. This is reasonably technical, so unfortunately, I cannot give you much more than what I've said now. Okay, so you have to take my words for it. So. Okay. So one model that I wanted to give you again that you all know is the Bohr model, because the Bohr model is very fruitful to recover all the power laws. So essentially, you just assume that you've got your nucleus, you've got a circular trajectory. You just write, of course, that there is an attraction, a force, which is E squared divided by R squared. This is the force. And you just equate in the Bohr model the fact that the centrifugal force is equal to the Coulomb force. And that's Newtonian mechanics, which of course is completely wrong in the atomic world, but it doesn't matter, it gives the right scaling. And the second thing which is important is to say, that this is the Bohr quantization condition, is to say that the angular momentum is quantized in unit of h bar, with n, which is a principal quantum number ranging from 1, 2, and so on. So with this, you can eliminate V, and you will find R, which is n squared times m h bar square over E square. I remind you, E square is always my Q square over 4 pi epsilon naught. Okay? Good. So the scaling, you can find it here again. Okay? So is there anything else to say about that? No, I don't think so. Okay, so now the consequence of this very large radius are twofold. The first is that an atom in a Rydberg state has a reasonably long lifetime. The scaling goes like the cube of the principal quantum number. You can try to, I mean, as a problem set, you can try to derive those scalings. So it means that for n above 60, the lifetime of a given Rydberg state, which is to say the time it takes to decay to lower state, is on the order of 100 microseconds. So this is not super long, but it is long enough to do experiments. I will come to that tomorrow. The second thing, which is essential for what we're going to discuss, is that, of course, if I just take two states, nearby states with different parities, as we discussed yesterday, and they need to have different parities so that it's non-zero, the dipole matrix element scales essentially like the size, the classical size of the atoms, the n squared. Okay, so this is this very important scaling that allows us to have very strong interactions between the atoms. I'll come to that in a minute. So the consequence of these large dipole matrix elements are twofold. The first is that it's very easy to polarize a Rydberg atom. A tiny electric field, whether DC or AC, is going to induce a huge dipole. And second, they will exhibit very strong interactions. Okay, and those are the two properties that we use and that are fruitful for to do quantum simulation or anything with the Rydbergs. So this is, once again, something, do it as a problem. Use the scaling that we just discussed before and try to recover all those scalings. I mean, the first one is already given, but you can try to recover all those scalings. And in principle, and in particular, try to recover this wild scaling about the C6 coefficient of the van der Waals interaction scales like the 11th power of the principal quantum number. This is a pretty wild dependence. There are not so many laws that are so strongly depending on something in physics, apart from the exponential law, obviously. But just try to derive this based on what we discussed yesterday. And we can discuss the kind of solution either on Friday or tomorrow at the beginning of the lecture. So problem, said, do it. Okay? from yesterday's discussion, it will imagine that a larger dipole moment would lead to a larger spontaneous emission decay, but it seems like, so an excellent question, but you are forgetting one thing. Gamma is indeed dg square, but there is also an omega cube. And the higher you go in n, the smaller the omega. And actually, this scaling here is 1/n cube in energy. You need to cube that times dEg, which is the square, so n to the 4th. Okay? Francisco, you happy with that?
Yes, so just making sure. So that the increase in the dipole moment is not with what we define as sort of the ground state or sort of like low n, but actually with like the nearby states. That's
Yes.
the okay.
Yeah,
Thank
well,
you.
I mean, well, it's more subtle than that. Essentially, there are two ways. You can have either, so this is a given Rydberg state. This is the ground state. An atom can essentially drop to lower state through something which is close to an optical transition, or it can decay back to a nearby state. What I've calculated here is this. The scaling is n to the -5 for the lifetime. For the decay rate, sorry. But this one actually scales differently. It scales like, this is this thing, like n cube, the lifetime. It's just that the matrix element connecting this and this also goes down as n increases. Okay. Yeah, there is a lot of an each of the thing we spend 10-15 minutes, so that's the okay. But just try to fill and to recover those scaling laws. I mean, you have all the ingredients to do that in what I've discussed so far. So it's a nice problem to do. Okay, so I will move on this and just people have started to look at Rydberg states essentially since the beginning of AMO physics, but the idea that you could use as, I mean, to your interest, for some kind of purposes, the strong interaction between the atoms is an idea which is reasonably new. Actually, it's something that was promoted by Misha Lukin and Peter Zoller essentially around 2000. And it took an extra like 10-15 years to actually build experiment demonstrating that. So the basic idea, which is the very important idea, is the idea of the Rydberg blockade concept and mechanism. So this is the following one. I'm going to assume here that each atom now only has two states, the ground state and the Rydberg state, which I pick up and which is the well-defined Rydberg state. So essentially, this guy here is an NS state. Okay, it can be an NP, it can be whatever you want. It's a Rydberg state. Those two things I can excite with a laser. I will come back to that. I don't know when now. It was supposed to come back to that half an hour ago. So now it's probably going to be tomorrow. But essentially, I can couple those two states with laser, and I can excite an atom to a Rydberg state by a laser. Now let's draw the spectrum of the interaction spectrum of the two atoms as it's drawn on the right here. So you can have the two atoms in the ground state, one in the ground state, the other one in the Rydberg state, or the two in the Rydberg state. But what we've learned is that when two atoms are in the Rydberg state, they've got a gigantic energy. So essentially, this guy is the C6/R6 coefficient that scales like the 11th power of the principal quantum number. So true enough, you've got a little bit of van der Waals interaction here and here, but it's completely negligible with respect to the one in the Rydberg state. So as a consequence, I totally neglect the tiny van der Waals shift in those two states and only consider this one. So now the idea is, the idea is that if we excite or we set the laser on resonance to the excitation of a single atom, so either the first one or the second one, then if the atoms are close enough, you will find that you cannot excite the second atom. Okay, so this is called a blockade. So the atoms are close enough, and the bandwidth of the excitation, which is set by the Rabi frequency of the laser, is not enough to be able to excite this potential curve. So you either excite the first one or the second one, but never the two at the same time. This is the blockade. Why is it interesting? It's interesting because if you do not know which of the two atoms you excite, you end up in having exciting a superposition of the first one or the second one, which is an entangled state. So this blockade idea is fruitful because it automatically leads to entanglement. Okay, so that's the reason why people were kind of excited about this idea. The thing which is nice on top of that is that it's reasonably robust with respect to fluctuation in RB, because even if they move a bit, this potential curve may wobble a bit, but it doesn't matter. As long as it doesn't wobble more than the line width of this, you will never excite the pair of atoms. Okay? So this is this idea of Rydberg blockade. And so this idea was looked at very reasonably soon after the proposal came out. First in atomic ensembles. Each of the experiments would need like 15 minutes to be described, so I'm not saying that. The first time it was done on 2 atoms was at the Institut Optical and in our group and at the University of Wisconsin, so more than 10 years ago, and I'm going to discuss that a bit more later, most likely tomorrow, actually. Okay, good. All right, so do you have any questions?
There were a couple of questions still in the chat.
Okay, so are there special value for n that are typically selected among n equals 60 type states? No, I don't think so. Essentially, in our group, we are using any state from 60 to, let's say, 85 or 90. Why do we pick up one particular state with respect to another? It's always a compromise of between not being too sensitive with respect to electric field, but still have a strong interactions between the atoms. Yeah, so it's a bit of, essentially you can do if you have a very good control over your experiment, you can do whatever you want by picking a Rydberg state between 60 and 90. If it's a perfect setup. Now, of course, it's never a perfect setup. You cannot necessarily bring the atoms close enough, and therefore you will need to crank up a bit the n so that they have enough interaction energy and vice versa. Is the blockade method restricted to 2-body interaction, or can we use it to go beyond 2-body? Yes, we can. So essentially, I can generalize this idea. Now, if I just place many atoms in this Rydberg blockade radius, I can place one and only one excitation in this, and therefore what you have is a state which is 1 over root n RGGG plus RGG, GRG, and so on. Okay? So yes, indeed, you can generalize that. You can place one and only one excitation within a Rydberg blockade field. So n is the number of atoms within this field. So you can generalize that. And can we create the antisymmetric RG minus GR state? Yes, we can. Well, it's a bit more complicated because if you want the full truth, then it becomes ugly. There are things that I've forgotten here on purpose. You have the phase factor that comes from the laser beam creating the excitation. So here it would be e to the I chi R1 because you excite the first one, chi R2, and so on and so forth. So if you have a geometry which is very well specified, and you know exactly within sub-nanometers where the atoms are, which is impossible to do, in principle, you can pick up the phase factor by choosing the geometry and excite the symmetric state, the antisymmetric state. Okay.
I have a quick question.
Sure.
So you just mentioned that one thing you think about regarding which end you take is like not having too much sensitivity to electric field.
Yes.
So like being that these Rydbergs are like these really big dipoles, like does it matter that these vacuum systems are at room temperature and you have a bunch of black body radiation around? Or is that kind of not important?
No, well, it's a very good question. It does matter. So essentially, when you calculate the lifetime of Rydberg atoms, half the lifetime comes from the decay from the Rydberg to the ground state. The second half from the black body radiation that triggers this transition. So essentially, if I say you go from n to n minus 1, this is the scaling that we did with Francisco like a minute ago. So this is this n to the 5. But I mean, if you calculate the lifetime of this state, it's tiny. Sorry, it's not tiny, it's very large. So essentially, it shouldn't be a problem. But the problem is that you have black body induced decay. So you do have the average number of photons, so let's call it n photons so that it doesn't look the same. So this is the number of black body photons. So these bring these things to typically about 100 microseconds. So if you want to reduce or to increase the lifetime, you need to suppress the black body radiation. Okay, so we need to work at 4 Kelvin, which is something that people start to work on now. Yeah. Does it answer your question? Or?
Yeah, yes, thank you.
Okay. So now let me try to start at least discussing briefly the interactions between the Rydberg atoms. Now that we have that, and essentially trying to walk you through the van der Waals interaction and the resonant dipole-dipole interactions. I still have 10 minutes, is that correct? Or Leo or Anna, about?
Yeah, that sounds good. Yeah, that sounds
okay.
Yeah.
So once again, a few references that
you also had a lot of questions, so
Yeah, so you can keep using the time.
Yeah, but
what I was suggesting is no problem to go to the very end because you had a lot of questions during the lecture, so which is
sure, but I mean, it's part of the game. I don't want to fry anyone. I mean, questions also are very okay, so very technical things. It will be kind of helpful to understand tomorrow's lecture, but essentially, how do we do the Rydberg excitation? So we do it with lasers. So essentially, you start from a well-defined internal state of the atoms, the ground state. You can do that by optical pumping the atoms in a state, which is, so I'm using always rubidium as an example because this is what we have in the lab, but this is totally standard for any alkali. And essentially, you do what is called a two-photon transition. So you just pile a laser at a given frequency with a laser at another frequency, and usually, contrary to what is written here, they are detuned. So the blue arrow should go around here. So essentially, if you do all this, and you have the Rabi frequency blue and the Rabi frequency red, and you are away from this state, the intermediate state, you can completely neglect the spontaneous emission and assume that all this is equivalent to just two levels that are coupled by a laser at a given Rabi frequency. This Rabi frequency omega now, this is related to the effective, so the real Rabi frequency of the blue and red laser divided by the detune. Okay, so now, so that's the first thing. You can actually drive coherent Rabi oscillation between those two states. So essentially, you prepare the atoms in this state, and you drive with this laser, this combination of two lasers, and essentially, you have a Rabi oscillation between those two states, as here. Okay, we can discuss a bit more the experimental detail, but I will defer that to tomorrow now. For the moment, just think of it. I have a two-level system. I drive a Rabi oscillation, and indeed, it's a coherent drive, as you can see here. The only important thing is that it can be done at a reasonably fast frequency, typically a few megahertz. Okay, you can also, it will be useful tomorrow, manipulate microwaves. So essentially, what you can do is to prepare an atoms in a given Rydberg state and drive a microwave transition between this particular Rydberg state and a nearby one separated now by transitions which are typically in the gigahertz. Okay, and so that's again an example of a Rabi oscillation between this state and this state as a function of time when you apply the microwave, which is tuned onto this transition. So those are the two kinds of coherent manipulation we can do in the context of Rydbergs. Okay. Okay, so this I will drop, sorry. All right, and so now essentially, I would like to discuss briefly the different interactions that we can have. So now, that's going to be useful for tomorrow. Essentially, you can have two types of interactions between Rydberg atoms. And those are the two types of interaction that we have encountered and derived yesterday. So essentially, you can have the first one, which is the van der Waals interaction. And that's the interaction that occurs when you just take two atoms, and those two atoms, you place them in the same Rydberg state. So in this case, what happens is that there is a shift in energy by an amount, which is what we have derived, the C6 over R6 of this Rydberg state. With the C6, once again, with scales like the 11th power of the principal quantum number. Okay? The second thing that we can have as an interaction is the resonant interaction. So essentially, one atom will be excited to a state ns, the other one to a state n prime p. And you have this degeneracy. It was the EG-GE of the toy model yesterday. And the consequence is that you have an energy split here by an amount, which is C3 over R3. Okay, those are the two kinds of interactions, and we will play with the two of them tomorrow. Okay, so let me just very briefly show you the dynamics of a pair of atoms going between independent atoms to the Rydberg blockade, and also show you how you can infer from that the interaction energy between the atoms. So let's again, so this is the very same slide as the one I showed you to illustrate the blockade. So the thing which is important to realize is that if we are in the Rydberg blockade regime, essentially I cannot excite the two atom potential. So I can only excite one of the two atoms. So I have this 1/√2R. So now the thing which is very important is that if omega is the Rabi frequency that couples G to R for a single atom, when you have now your two atoms that can be excited between ground, two atoms in the ground state, or this entangled state, you will enhance the Rabi frequency by a factor square root of 2. Why is that so? Because now if you calculate the total dipole of the pair of atoms, GG 1/√2 EG, RG plus GR, what do you have? Well, you will have something which is G D1 R/√2 plus the same thing for the second atom, G D2 R for the second atom. And this is just omega, if you wish, the Rabi frequency, which is proportional to the dipole, times 2 divided by √2. So you've got an enhancement by a factor square root of 2. So now the two atoms behave as a single entity, which has a collective dipole, which is enhanced by square root of 2. Okay, so in the blockade regime, you have these enhancements of the Rabi frequency. So let's try to see what happens if I just take two atoms and I try to excite them in various regimes. First, I just take my two atoms and take them very far from each other. In this case, if I try to drive them independently to the Rydberg state, I obtain on the experiment this kind of oscillation as a function of time. This oscillation is what? This is the sine square omega t over 2 that you learn from the Rabi frequency. But now, each of the two atoms oscillate independently from the other one. So the probability to excite the two atoms in the Rydberg state at the same time, when they are very far from each other, so they do not interact, is just the product of exciting the first one times exciting the second one. So it's a sine to the fourth. And indeed, this is what you observe. This is not a sine, it's flatter than a sine square here. So indeed, this is this curve. Let's take the opposite limit, where the atoms are very close to each other. And now I plot the probability to again excite the two atoms at the same time. This probability is near 0 because I'm in the blockade. This is exactly what I want to see. Of course, as an experimentalist, having 0, you can always say, well, you've forgotten to send the laser, and so it will give you 0 as well. So you want to make sure that something is happening. And so in order to check that something is happening, you plot on the very same set of data other types of probabilities. You can plot the probability to excite one and only one atom. If you are in this first regime here of non-interacting atoms, this probability should be the product of exciting the first one and not exciting the second one, plus vice versa. And this is essentially this curve that oscillates twice faster. Now, if you are in the blockaded regime, you find Rabi oscillations enhanced by a factor square root of 2. So the ratio of the oscillation between here and here is actually square root of 2. So that signs the fact that indeed your two atoms behave in a fully coherent way, if you wish, and that they are blockaded. But you can do something even more interesting. Let's now work in the intermediate regime, for which I'm neither fully blockaded, neither fully independent. Then if I do that, of course, the dynamics is going to be much more complicated. Instead of being governed only by omega, I have two energy scales in the problem. I will have omega and the interaction energy. So now the dynamics, the state will be psi of t, which is something like alpha GG, plus beta 1/√2, if you wish, GR plus RG. But I also have plus gamma RR. So it's not only, and these states does contribute now. So if we do the experiment and we work in a regime where indeed the Rabi frequency is on the order of the interaction energy, what you find is this kind of bizarre curve, which has some weird oscillations. But now let's do a simulation by the Schrödinger equation. It's a three-level system. So essentially what I do is I calculate the solution that I just showed here with the Hamiltonian, which is nothing but 0, the energy omega, 2 times omega 0, plus u, the shift, and I have the omega, the omega, the omega, the omega, in a nutshell, omega square root of 2, omega square root of 2. So essentially you can write everything. It's just a three-level system. You solve this problem, and this is the kind of curve that you get from the, if you want to simulate this. So you see that now, you fit many of these oscillations for various interparticle distance, and you are able to extract the interaction energy between the atoms. Okay, so that's one way to measure the interaction between a pair of atoms, and this is something we've done. So now you repeat the experiment for many distances, and you infer from this coherent oscillation, which is modified by the interaction, the interactions, the van der Waals interactions between two atoms. Okay? All right. Do you allow me an extra 5 minutes so that I completely wrap up by describing the last resonant interaction, or is everyone fried and would like that we stop? We just need 5 minutes, but questions or?
Well, how are the students feeling?
Yes,
I can
because
also
we have all, I mean, maybe for my suggestion is to stop here. We have the lecture tonight, so
Yeah. No, let's stop here. I agree.
Let's stop here. It's been really clear and very and a lot of information. So maybe this is
yeah. Sure.
It's great. It's great.
And also we can maybe instead use that 5 minutes to ask questions, to discuss and
Yes,
ask
please
questions.
go ahead. Yes. So there were actually many questions that popped in.
There is one.
No, there is one, and it's an important question. So essentially, so the question of Weibav, I don't know if I pronounce well, it seems like the matrix element for Rg minus Gr actually vanishes, indeed. So now let me again do the spectrum. So I have Gg, Rg, Gr, Rr. Okay, but of course I can also choose another basis. I can decide that this guy is 1 over root 2 Rg plus Gr, 1 over root 2 Rg minus Gr. So it's a basis which is orthogonal to the first one, right? I have Rr and I have Gg. And so indeed here I'm going to find omega square root of 2, while here I'm going to find 0 based on the same argument. So this is actually the reason why I'm saying it's just a three-level system. I do not need to consider this state. It's not coupled, actually. It's a dark state. Does it make sense?
Can I ask a follow-up question regarding to
Sure.
this?
Francesco, you go ahead.
How does this work when I start considering more atoms? Like, I guess, like, will there always be such a dark state? Maybe
Yes,
this
there is
jumping.
always. No, it's again an excellent question. It turns out, let's do it. I have R, G, G, 1 over root n, all this. And then, of course, I have other states here. And it turns out that this one has a coupling which is omega square root of n, and all the others are actually subredient state. So these arguments can be made totally general. So you can, so that's something, you can try to do this, and you will indeed find that if you use this symmetric basis, all the other states need to be antisymmetric and therefore give you an average dipole of 0. So at the end of the day, no matter how many atoms you have, you can only boil it down to just one collective state, which is 1 over root n RGG plus all the other things.
Thank you.
Yes, I'm trying to give you a hint of the demonstration in like 10 seconds. The problem is that in 10 seconds, I don't manage to do that. So but we can discuss that a bit more if you wish during Friday's session or any time. So.
It seems like that should depend whether the atoms are bosons or fermions.
No, it does not, because what we are talking about here are internal degrees of freedom. So essentially, whatever the atoms are, it doesn't matter. They are always particles carrying spins, if you wish. Those are two-level systems. So those systems, actually, the mapping is onto a spin 1/2 system. And spins are neither boson nor fermions. They are spins.
I think a better picture is a decay manifold picture where you classify the atoms by the total S. So that atoms with the maximal symmetry has S equal to n-half, n in the number of atoms. That is and the other states start to diminish S from n-half to 0. For two atoms only, you have S equal to 1 and S equal to 0. And that's why only you have fully symmetric and antisymmetric. But as you go for more atoms, you are going from S equal to n-half until the S equal to 0 manifold.
But once again, for what we're discussing with the Rydberg, fermion or bosons is irrelevant.
Are the same, exactly. No, this is just the collective spin of a spin that is statistics is not not important, but you can classify the spin states, no independent of quantum statistics, just by a quantum number that is associated with the symmetry of, but it's not quantum statistics. It's S equal to n-half. You have fully permutational states between the spins. That's the triplet or the states that have exactly coupling the square root of n because are fully symmetric. But then you can have the antisymmetric state that is the singlet or that is the S equal to 0, independent of statistics. Statistics might be tight when you start to think about atoms very close to each other. That's not the case here. When you can have a fully symmetric state or antisymmetric, and you can tie between the spin and an internal degree of freedom and the spatial thought. But for the atoms separated at the twister level, it would never be important, the quantum statistics. But you can understand just by the total S a little bit more the couplings of the light with the atoms.
Other questions?
So I've always seen that, like with Rydberg atoms, everyone talks about Rydberg blockade models where you can excite one but not the other. I guess you can also just shine light such that you excite two at a time, right? Is that possible?
Yeah,
and then you can have terms like sigma plus or something like that.
Yeah. And so that's what we'll do tomorrow. Yeah, the problem now, those days, it's a bit bizarre, but everyone associates Rydbergs with Rydberg blockade, and that's not at all the same thing. Actually, most of the interesting experiments, so to speak, are done outside the Rydberg blockade regime. There are cases where you do want to have the Rydberg blockade. If you want to create a gate, if you want to create entanglement, you need the blockade. But if you want to do many-body physics, you want all the energy scales in your problem to be on the same order. So you want U, the interaction energy, to be on the same order as omega, the drive. So you are precisely away from the Rydberg blockade. The Rydberg blockade is the simplest situation because essentially you do not care any longer about the interactions between the atoms. They dropped out of the problem. Okay. Bon, but then tomorrow we'll discuss a bit more. So we'll finish off with the resonant interaction and we'll discuss more examples of many-body simulation. It will just be, I mean, of course, I won't go into the detail. That will be like 10 lectures or 3 hours each, but I will try to give you a few examples of what people have done around spin models, just to give you a flavor of the kind of physics you can do with that. Okay.
So maybe this is a good time to break. We have Eric Cornell's lecture coming up at 11. So I'm going to stop the Zoom and then let's tune back in at 11 o'clock in about 22 minutes.
Yeah, thank you, Antoine, for the fantastic.
Thank you, Antoine.
Thank
See you tomorrow. See you, everyone.
Thank you so much.